Hey you all, so in this video I'm trying to do three things. I'm going to review derivative rules, remind us what these calculations are actually calculating, like what is the point of this work, and then just demonstrate how we can find the equation of a tangent line. So let's start with, so if I solve this problem, I have f of x is equal to x to the fifth plus 2x to the third minus x squared. If I was going to find this derivative, technically the first thing I should do is apply like my derivative rules. This expression, you all can clearly see I have three terms. The first two are being added together and last term is subtracting off. So if I was going to write this expression, I would most commonly use f prime notation. But for this, I will use the ddx notation, which is saying the derivative of this function with respect to the x variable. We will actually learn how to derive with respect to the y variable, which is pretty cool. And then if I was going to properly apply my derivative rules, I would start by saying, applying like the sum and difference rule, that I can find the derivative of a function of a polynomial by finding the derivative of each individual term separately. So what I'm arguing is this, that the derivative of this f of x function is equal to the derivative of x to the fifth plus the derivative of the function 2x to the third, and then minus the derivative of x squared. And technically, I could put it in parentheses if I wanted to. I could say the derivative of these functions, but it's not absolutely necessary. And so now I'm going to apply each derivative rule. Well, for the first term, I can just apply the power rule because there's no coefficient for the x. So I could say that the derivative of the function f of x is equal to applying the power rule to this term. The power rule is just x to the n. The derivative would be coefficient comes down, and we subtract 1 off from the exponent. And so I bring the 5 out in front, and I would say x, and then 5 minus 1 would be 4, and I've derived that first term. Now for the second term, I should technically apply the coefficient derivative rule, where I first rewrite this, bring this down here, where I'm first arguing that this derivative would be, 2 would be out in front, and then I would derive the remaining term x to the third. And so it's really saying 2 times, if I apply the power rule, 3 times x, and then 3 minus 1 is 2. So this derivative term would be 6x squared. Of course, I think you all saw we could jump a lot faster than that. That's kind of the idea of like applying that actual derivative rule. And then lastly, I would apply the derivative, or I'd find the derivative of x squared. The minus sign would stay the same, and the 2 comes down, so it's 2, and then x to the 2 minus 1 is just 1, so I can leave it just like that. So I could represent, like, this is the derivative of the f of x function, which I could also represent in prime notation. Now, what I just showed you is just reminding you what the actual derivative rules are for a polynomial. But what I did, you should not do. Like, you should not spend your time actually applying the rules to each term. And you won't see most of our learning do that in the future. Like, if I had these derivatives, if I wanted to say what the derivative of g of x is, I would say g prime of x is, and just apply the power rule quickly to each term. And then the derivative of a constant is just 0. So I don't even put the plus 0. And that's it. And then similarly, if I found the derivative of this f of x function, just going to be 2x and then minus 6. So a reminder of what we just did, we just found expressions that describe the slope at any point, any x value on the original function. And that's what derivatives are, like they're expressions that can describe that instantaneous rate of change at any point in time that we're curious about. So if I had the question for you all, like, okay, what is g prime of -1? What I'm really asking is, hey, what's the slope on the g of x function when x equals -1? And we could now tell that, figure out that answer really quickly just by plugging in that information into our derivative function. So if I just replace every x value with -1, then I'm arguing that, well, the slope on the original g of x function when x equals -1, -1 squared is 1, so this would be 3, and then negative negative is a positive. So we're saying that the slope when x is -1 on the original g of x function is 16. So it's a really steep and positive slope. So it must be a really steep part of the function. And then similarly, if I wanted to know the slope on this f of x function, let's say at x equals 1, I could wonder about what is f prime of 1, and that's just going to be 2 times 1 minus 6. So we're saying that when x equals 1 on this f of x function, this quadratic, the slope must be -4. Okay, and the last part of this video, I want to respond to my third objective, which is showing off how we can write the equation of a line that's tangent at a certain point. So this is the last function we worked with on the very last example we just did. And this is a function you all saw all throughout your math career. Now, this function is a quadratic. We know it's facing upward because the a value is a positive value. If we factor it, it would factor to be x minus 5 times x minus 1. So it has x-intercepts at 5 and positive 1. We could also, if we wanted to, find the vertex. You see it right there. We could have also found it without looking at it. We could use that expression negative b over 2a, which I know you all saw in Mr. Schreischen's class. And that would give us that the x value is 3 of the vertex, and we plug in 3 to find the y value. So it's a function you're pretty familiar with. And we decided that the derivative of this expression was 2x minus 6. And I put y equals just to graph it. And it might not be obvious right now how this line connects to this function, and we'll learn about that in the coming chapters. But like we said, if we wanted to know what was the slope of this line when x is 1, then we just plug in 1 for x. And we can kind of see when x is positive 1, it kind of makes sense. It's a negative slope. It looks pretty steep, so -4 seems like a reasonable slope. What's really cool about Desmos is you can actually type derivative language, and it'll give you that derivative function that we just saw automatically. So use that power for good and not evil. But it's really cool. Desmos has a lot of really cool functions. And so let's say we were curious to figure out, well, what is the equation, not just the slope, but what is the equation for the line tangent to this function at x equals 6? Well, reminder, our most basic form for a line is y equals mx plus b. If I want to write the equation for a line, I need the slope, I need the y-intercept. But what's really cool is that the derivatives are calculating the slope at a given point. So let's first start there. Reminder that this y equals just 2x plus 6 rather is the derivative, 2x minus 6 is the derivative of f of x. So if I wanted to know, okay, what's the slope right when x equals 6? Well, I just want to plug in 6 for this value, for my x value. And that's just 6. And so we're arguing that right here, when x equals 6, which is the point 6 comma 5, we're arguing the slope right at that value is 6. So I'm arguing so far that my slope equals 6. And so now to figure out the equation for this line, I just have to know what is the actual xy value on that on the function. Now clearly we can see, all right, I can look at it, but let's say I didn't have a function. I could still plug in into my original quadratic. I could plug in 6 squared minus 6 times 6 plus 5. That's going to be 36 minus 6 plus 5, which gives us that same 6 comma 5 for the actual points. Again, we can still find points by using regular function notation, plugging in input values to find output values. And so if I want to write the equation for this line, I would start by saying y equals 6x plus b, and then just plugging in the point that I know. Again, the x value in question is 6. The slope just happened to be 6. That's a coincidence in this case. And the y value is 5. So this would really be 36 plus b equals 5, and I subtract 36 on both sides, I would get b equals -31. And so what we're arguing is this. Oh, it's really cool. Desmos actually plugged it in right away for me, so I didn't even think that was going to happen. But notice how it actually substituted my variables, and it gave me the equation for this tangent line. When I actually write it for you, y equals 6x minus 31, check it out. This line, I'll zoom out a little more, you can see is very much tangent to this function right where x equals 6. Looks like it just, let me zoom in one more, looks like it just barely touches it right there. And then it only touches at that one point. And you can see it gets close everywhere else. But that's what's so cool about derivatives is we're actually able to approximate the slope on a curve, which we couldn't do before. And we're actually able to write an entire equation for a tangent line to really get an idea of what is that slope value, and can we show that there is indeed a line tangent at a given point. I hope this was helpful. As always, let me know what your questions are, and believe in yourselves. I believe in you. I'm here for you.